So we're on question 4 of homework 14, and this question basically uses something called the Chernoff bound to calculate deviation from the expectation of the sum of independent and identically distributed Bernoulli random variables. So Chernoff bound, basically Chernoff inequality, basically uses the monotonicity property of the exponential function. And interestingly, it uses the weak Markov's inequality to actually give a very tight bound by using by optimizing over some values to get the best possible bound. So let's see how that works out as we work from question 1 through question 9. So question 1 asks us to, question 1 basically establishes how good Chernoff bound is by using Chebyshev's inequality to calculate something. So first of all, it says, to help you understand, let's see what the exact probability is. The expected number. Use a computer to calculate the exact probability. So the exact probability, since this is a binomial distribution, you can just plug in binomial underscore CDF. In MATLAB, it's called binom CDF. I think binom CDF, I'm not sure, you can check that up. You have to enter the number 80, and you have to enter the number as in you want to find the CDF up until what point? 80. And then you enter n and p, which is a half, right? And then it gives you a number, which is the binomial CDF. But you want the probability that it's greater than or equal to 80, and the CDF gives you the probability that it's less than or equal to 80. So you take 1 minus this value, and this gives you 5.58 into 10 to the negative 10. That's the probability that you will deviate, you will go above 80 in the sum of n Bernoulli random variables when the number of tosses is 100, and the probability of each toss being ahead or taking the value 1 is 0.5. Now let's use Chebyshev's inequality to find out the same thing. Chebyshev's inequality says the probability of s greater than or equal to 80 is equal to probability of s minus the mean, which is 50. That looks a little ugly. 50 greater than or equal to 30, right? Now we're just bounding the probability that it deviates from above the mean by 30, which is less than or equal to, let's take the absolute value of this, because now we're weakening it by bounding both sides. This is less than or equal to, from Chebyshev's inequality, variance of s divided by 30 squared, which is 100 times p times 1 minus p, which is 0.5 times 0.5 divided by 900, which is equal to 0.0278. So you see how far away this bound is on an exponential scale from this. This is something on the order of 10 to the negative 10, and this is 2.78 times 10 to the negative 2. See, there's such a big difference between these two powers of 10. So this tells you that Chebyshev's inequality is actually a very, very, very bad bound. And yeah, so that's it for question 1. Now we'll try to work through the other questions to see how much better Chernoff bound is. Now for the second question here, we have to show the independence of, let's say we have a function which goes from the domain of binary alphabet and maps. It's a function from 0, 1 to all real numbers, right? And we need to prove that if xi to xn are independent, then f of xi to f of xn are independent, right? So let's look at two cases in this, okay? So we have to prove, what do we have to prove? We have to prove probability that f of xi, f of x1 is equal to a1, let's say, comma, f of x2 is equal to a2, all the way till f of x is equal to an is equal to just the product of I is equal to 1 to n, probability of f of xi is equal to ai. That's what we're trying to prove to show independence. So let's look at it in two cases, right? So we know that the function takes only 0 or 1 as argument. Now the two cases are that case 1, that out. Two cases are that both the function maps both 0 and 1 to the same point, or rather, okay, f of 0 is equal to f of 1 is equal to c, or the second case would be where f of 0 and f of 1 are not the same. So let's see how this works out. So let's look at case 1 now again. Now, this case is rather trivial. So what this says is that in this particular case, we have f of x1 is equal to a1 comma f of x2 a2 all the way to f of xn is equal to an if and only if for all ai is equal to c. Only if every single one of these ai's is equal to c, only then will this probability make sense, because otherwise we know that f of 0 and f of 1 are always going to be c. So if any of these values are not going to be equal to c, then you know that's not going to happen. And the probability of that sequence, even if only one is not c, that probability of the entire sequence is equal to 0, is equal to 1. Okay, so it's equal to 1 if and only if everything is equal to c, and equal to 0 otherwise, right? But what is the right hand side in the thing on top here? It's just the product of these is going to be the product of each and every individual f of xi to be equal to some ai. And if any of those ai's are not going to be equal to c, that particular term in the product of all the terms is going to be 0 again, right? So probability of xi, f of xi is equal to ai is equal to 1 again if and only if for all ai is equal to c is equal to 0 otherwise. Because the moment any of these ai is not going to be c, then that particular term is 0, and when you multiply 0 to all the other terms, everything is going to become 0. So it's just as the thing above. So these two are 1 if and only if all the ai's are equal to c. Therefore, if all the ai's are equal to c, those two are equal to each other. And if any of the ai's are not equal to c, they're not equal to each other. Therefore, if both f of 0 and f of 1 are the same number, then both these map to the same thing. So therefore, for case 1, our condition for independence is satisfied. Now let's look at case 2, where f of 0 is equal to c0, comma f of 1 is equal to c1, c0 not equal to c1. That's our new case, or that's the only other case. Now if f of 0 and f of 1 are distinct, what you can do is now you can restrict your codomain, or the set of all numbers that your function can hit. Not the range, but the codomain. Well, in this case, the range will be the codomain. So we can just say that instead of f being a function from the binary alphabet to r, let's make it a function from 0, 1 to c1, c0, c1. Now, why can we do this? Because we know that the only two arguments f can take are going to be 0 and 1, and the only two outputs it can take is c0 or c1. So this is enough to completely define f. So we can do this, and we know that f of 0 is equal to c0 and f of 1 is equal to c1. So now we can define an inverse function, right? F inverse of c0 is equal to 0, f inverse of c1 is equal to 1. Why can we do this? Because you can define an inverse if your function is injective and surjective. That is if injective means that every unique element here maps to a unique element in the right side. So every unique element in your domain maps to a unique element in your codomain. And surjective means that every single element in your codomain has been mapped to. So if those two properties are satisfied, which they are in this case, then you can define an inverse. So you can take an inverse of c0 is equal to, and you can define f inverse to be f inverse of c0 is equal to 0, and f inverse of c1 is equal to 1. Right? And the key point to note here is that probability of f of x is equal to f of x for some random variable x is equal to some let's say C bar, where C bar is either C0 or C1, is equal to the probability that F inverse of C bar is equal to X. Because the function is invertible, F is invertible, then these two are equivalent. That is, F of X is equal to C bar if and only if F inverse of C bar is equal to X. So therefore these two events are the same, and this forms the basis of how we're going to go about proving this for case 2. So now let's take the I'm going to erase this, and I'm going to take the left hand side. Probability of F of X1 is equal to A1 all the way to probability of F of Xn is equal to An can be written as is equal to probability that F inverse of A1 is equal to X1 all the way to F inverse of An is equal to Xn. Now this, since we know that all the xi's are independent, we know that probability of xi is equal to something, comma probability of x2, so probability of xi is equal to something, comma x2 is equal to something, all the way till xn is equal to something, is equal to just the product of the individual probabilities. So this is equal to a1 is equal to x. I think I should write it the other way around to make it slightly clearer. x1 is equal to f inverse of a1 all the way to xn is equal to f inverse of an. Oops, I didn't actually use independence yet, but I just rewrote it so that x1 is in front, so that it's a little clearer. So now this, because of independence of the xi's, is probability of x1 is equal to f inverse of a1 times all the way to dot, let's put that as a dot, probability of xn is equal to f inverse of a n, right? So now, since we knew that these two events are equivalent, as in f of x1 is equal to a1 is equivalent to f inverse of a1 is equal to x1, let's just do that backwards again. Let's actually go backwards now. So probability of x1 is equal to f inverse of a1 is equal to, again, probability of f of x1 is equal to a1. So we moved from f to the inverse of f, now we're moving back to f, times all the way to probability of f of xn is equal to an. This is just equal to product from I is equal to 1 to n, probability of f of xi is equal to ai. So these two shown are the same. So if xi's are independent, the crucial step which we need at xi to be independent is going from this step to this step. So what we did between these two steps is what we used, is where we used the fact that xi's are independent. So now we know that if all the xi's are independent, then any function of the random variables is also going to be independent. So that's it for part 2 of question 4.